Hello everyone, welcome to the CP 2021. My name is Liu Jun. I'm from Southeast University, Nanjing, China. Today we are going to talk about joint frequency in the recognized rating 2014 classification system based on field p-wave propagation velocity tests, a new rating method. Our report contains 5 different parts. Firstly, reduction. As a natural geological material, rock mass contains various types of visible damages, wherein cracks, holes, joints, fissures, and faults are examples. In our conference, the cracks are the same topic, but today we are going to talk about joints and its ratings in the RMR classification system. In the first picture, we can see there are low visible cracks and joints in entire rocks, and for rock masses, there are many visible joints and faults. Next, we will talk about rock mass classification systems. Today, there are many empirical classification systems. For example, basic quality in the Chinese national standard, rock mass rating, geological strength index, and RMR, and so on. Among these classification systems, rock mass rating, denoted as RMR, has become the most extensively used empirical system and an international accepted design tool. As we know in rock engineering, the randomly distributed joints control the behavior of engineering rock masses. For example, shearing behavior and deformation behavior. Hence, the joint frequency is a key point in the process of rock mass classification systems, particularly in the RMR classification system. Next, I will introduce the p-wave propagation velocity test. It is a non-destructive and easily implemented method that can be applied under both field and laboratory conditions. The equipment included in this test are acoustic detectors, vibration exciters, and receivers. Under field conditions, by this method, a much larger proportion of rock layers can be easily sampled. It is worth mentioning that the p-wave propagation velocity is only one field parameter for calculating the basic quality index of rock masses described in the Chinese national standard, engineering classification of rock masses. We can use the following equation to calculate the BQ value. In this equation, the RC means the uniaxial compressive strength of entire rocks, and KV is the integrity index of rock mass. And essentially speaking, the propagation velocity of the p-waves in a rock mass depends on a number of internal and external parameters, wherein the number, orientation, spacing, separation, roughness, weathering, and the type of filling materials for discontinuities is a key point. As a result, there is a high possibility to obtain the variations of RMR, sum of all the rating parameters as a function of the p-wave propagation velocity parameters. Still, there are also works on the individual rating parameter in the RMR classification system as a function of the p-wave propagation velocity, but few studies have been extendedly elaborated on directly determining the rating of the joint frequency. In the newly proposed RMR classification system by the easily implemented field P-wave propagation velocity test. Therefore, to avoid the occurrence of the secondary core breaks caused by tuning process and the difficulty in the parameter acquisition under some complicated conditions, it is essential to explore the joint frequency in RMR 14 classification system as a function of the field P-wave propagation velocity tests. Usually, if the ratio of the P-wave propagation velocity in the rock mass to that of the entire rocks is high, usually a low joint frequency in the inside rock mass is implied. Therefore, it is essential to explore the relationship between the inside P-wave propagation velocity and the joint frequency of a rock mass to indirectly calculate its rating in the RMR classification system. Next, we will talk about the second part. The RMR classification system has two variants. The most important one is RMR 89. And over the last 20 years, this empirical has been updated and known as RMR 14. One of the most important changes between these two variants of RMR is that the RQD spacing of discontinuities were unified and substantiated by the joint frequency, but the rating remains unchanged. That is, both accounts for 40% in these 200 mark systems. This simulation on the RMR initially intended to eliminate the difficulties in determining the RQD index from the excretion phases. Usually, the tuning process will cause core break, tuning breaks, and it is difficult to judge the breaks from the natural joints. Next, we will talk about the third part. From the Chinese national standard, we can find the relationship between the cubic joint count of rock mass and the integrity index of rock masses, wherein the cubic joint count JV is defined the sum of the joints within a rock mass within 1 cubic meters, and the KV is a ratio between the P-wave propagation velocity of rock mass and the P-wave propagation velocity of entire rocks. By this empirical relationship, we can employ the latest square regression method to obtain the empirical relation between JV and KV as follows, and we also draw the curve between these two parameters. Also, there is an important parameter of rock masses. It is called joint frequency. We can denote as ND here. For rock mass, if we want to calculate the cubic joint count JV, we can use an empirical coefficient alpha and the joint frequency by this equation. And there are two equations. If we select KV as a connected point for JV and the P-wave propagation ratio, we can get the following equation, i.e. the JV between the P-wave ratio. And next, by employing this relationship between the joint frequency one-dimensional to the three-dimensional, we can obtain the joint frequency in the RMR14 classification system by the easily obtained p-wave propagation velocity ratio. In our analysis, there is an important factor, i.e. the multiplying factor alpha. Since it is empirical, since it is experience-based, so for different researchers and for different conditions, the multiplying factor alpha is difficult. Is difficult to determine. For different distributions of rock joints, e.g., the normally or evenly distributed, the multiplying factor alpha equals to 1.665 to 3. For different value of alpha, we can draw the relationship between the p-wave propagation velocity ratio and the equivalent joint frequency ND here. And next, we can convert the origin rating regulation to our newly proposed method. In the RMR classification system, the rating of the joint frequency is dependent on the joint frequency, and in our method, the rating of joint frequency is dependent on the p-wave propagation velocity ratio. Next, we will introduce the validation and analysis. First, we have collected data sets from literature, and also we have tried to find our data sets from on-site test, but we failed to get our own field parameters. In the literature, the joint frequency and the joint conditions are described in detail, and we can give the ratings of the joint frequency and also the ratings according to the p-wave propagation ratio. Next, we will talk about the underestimates of our methods. It from two aspects. One is the empirical correspondence between JV and KV. Next is the multiplying factor alpha. Since it is a range comparison between JV and KV. Next, maybe in the future we can conduct the three-directional p-wave propagation velocity test. Summary and conclusion. One is the ratio of the p-wave propagation velocity in a rock mass to that of our entire rocks for joint frequency rating index in the RMR classification system. Next, our method underestimates the ratings of joint frequency. In the future, we will talk about how to elaborate this underestimation. Next, future we will conduct more field tests and collect more field data to enhance our the performance of our method. Okay, thank you very much. That's all.